All right, welcome everyone. Another day, another coding challenge. The stream is for entertainment purposes only, and let's see if we can crack another hard problem under infinite time. No, just kidding. We won't crack a hard problem under 40 minutes, but we will try to crack whatever problem possible today. All right, so let's see what we've got today. So pick one. All right, another hard problem. Oh my god. You are given a two sorted arrays of distinct integers, nums1 and nums2. A valid path is defined as follows. Choose array nums1 or nums2 to traverse from index 0. Traverse the current array from left to right if you are reading any value that is present in nums1 and nums2, you are allowed to change your path to other array. Only one repeated value is considered in the valid path. Damn. Return the maximum score you can obtain of all possible valid paths. Oh my god. Why always hard problems? I hate this site already. Why not just go easy or medium or whatever? No, three hard problems in a row. Whatever. Today, whatever happens, happens. I'm not going to spend all my time today trying to figure out what's the idea was behind this problem. So valid path is defined as follows. Choose array, any array, and traverse from index 0. So the minimum number of valid paths is 2. That's feels like that if you have two arrays. Traverse the current array from the left to right. Okay. From like this way, right? If you're reading any value that is present in nums1 and nums2, you are allowed to change your path to other array. Only one repeated value is considered in the valid path. So the last point, if I understand correctly, let's say I go from nums1, I hit 4. Now I'm allowed to go this way, right? But if I hit another 4 here, not 8, I won't be able to jump back. All right, so we need like how many valid paths, right? How many valid paths? All right. Let's say we have these two. Valid paths 2, 4, 5, 8, 10, 2, 4, 5, 8, 9, obviously. 2, 4, 6, 8, 9, obviously. 2, 4, 6, 8, then 10. Starting from nums 1 and starting from nums 2, obviously the nums 1, then you can again directly go to 5, then 8 and 10, then 4, 5, 8 and 9, and then 4, 6, 8 and 10. The maximum is obtained with the path in green is this. Output 30. So I should return the maximum score, which is the length, the maximum length of the valid path, right? Um, so it's not sum of all possible valid paths, but the maximum among them. Maybe too large? Why? It doesn't sound, it sounds like it's always linear. Why it can be too large? Ah, because the size can be almost like what? 10 million, and then we have 10,000 by 10 million, so some billions there. So they say, okay, just, do modular this thing. So, all right. So technically, we don't need to find all of the paths, right? We just need to find the path with the maximum value. But how do I find the path with the maximum value, right? Um, so if I will try to correct the label, so every time I start and hit 4 here, right, the maximum value here will be 2, maximum value here will be 0, then 5, then 8, then 10, right? If I hit 4 and I hit 6 here, I can hit it either from 4, and then it's 4, or I can hit it from 2, 2, 4, and 6, right? And in this case, the maximum value here definitely is this one. So I can try to keep iterating through the edges. And so obviously, what's the maximum value I can achieve at 2? It's always 0, right? Because n at 4 here is always 0. But for these 4, that can be where we can jump here, so we don't count this one. I can get 2 always, right? So what about 5? 5 here. So what's maximum weight I can get? So if I go this way, it's 4. If I go this way, it's 6. So to me, it's obvious that there is no need to traverse this path further, because if the maximum here is this one, right, like this, I don't care about this part. All right, so what about 8? Now I can hit it through 5, or I can hit it like this, right? So so it sounds to me, every time we move one step this way, right, we can calculate the maximum sum for every node that precedes it. Then we go here, maximum sum, and then somewhere at the end, there will be 2 maximum sum for this node and for this node. And because they're positives, right? So it's actually good that they're positives. Yeah, are strictly they're sorted as well. So I know then the earlier I jump. So how do we use sorted? So it's already clear that every time we move, right, to next number, we can check. So it will be basically, so how we can achieve 5 here? Either we can jump from this node, let's say, in this case, we say 4, right? And then it can be anything in this number. Ah, that's why it should be sorted, right? So we know as the sum of unique values in a valid path. Ha ha ha, it's unique values. All right, so let's go to the whiteboard now. Let me think a little bit on this. So let's imagine we have numbers like this, and we know that they're increasing. 1, 2, 3. 2, 5, 6, right? So the max here will be what? The max here will be whatever precedes this guy, whatever its max that precedes, right? Or this max. So it's max of max 1, let's say max 2. So it's max of max 1 and max 2. So we can have two arrays for nums1 max, num1, which will be size of num1 minus 1, right? Num1 minus 1, num1 m, let's call it. Sorry. Right? And we will have num2, and which is num2 minus 1. So this will store the max values. So they're sorted, right? Yeah, but the number of technically what we can do, we can say, okay, if this is 2 is located further away from the beginning than this, then maybe some preceding sum will be lower. But the problem is that all right, that we don't know what's this. So it looks like we do what? We do this way or n steps to compute max here and max here, right? So we do one by one until we can, right? So the nums I, so either 1 or 2, or let's say 1, 2, m That's why we need sorted. I got it. I got it. So the problem is, so the max for 2 will be max for this guy and max for this guy, right? So because they're sorted and they start with 1, this is the cycle we do. So we iterate through one array until and count the unique max until we hit this number, and then we iterate through second array and count this max until we hit this number. All right. The only thing I didn't get is how many times we can transfer in between 2 arrays. Let's say if I have 4, 4, 4, 4, can I? But it doesn't matter, right? If there is another 4, I can jump back here. And because it's sorted, so there may be 4, it doesn't make any sense for us to compute any further number for 4. So, I see, I see, I see. Okay. All right. All right. So, uh-huh. Mm-hmm. So then, technically, technically we don't need any nums here at all. All we need is for every number we have, like the prior number, let's say 2, 1, or whatever, it's sorted, right? That's what we remember. All we need is to find its maximum. Obviously, if it's 1, most likely it's just 1. So the previous maximum max is 1. So we say 2, right? And if 2, mm-hmm. Mm-hmm. So at most, we will iterate through. So the point is, I want somehow find numbers first that presents in both arrays, right? And put them into the queue, right? So we put them, we put them, we put them, we put them, we put them. I mean, unique numbers that presents in both arrays. And yes, so these are our traverse points, right? So 1 queue of numbers of nums belonging 1 and 2. Got it. So once we have this queue, that obviously will, because they're sorted, the queue will be sort of in the way that first in, right, will be then the first out, such that we start with small, because they're sorted, we'll start with the beginning. So we start with 2, let's say 3, 5, whatever. That's in both arrays, right? And then for every such number, we run our indices I and j for each of nums until we hit this number. And we don't, and once we go to the next number, let's say 3, we don't need to reset indices to initial 0 position, because we definitely know the 3 should be somewhere after. And then we find the max. Sounds like a plan. Let's see if it can be if it's realizable and if we can pass any time limit or whatnot. So we start with q of int that we call q. So let me see if I can q allocate size. And okay, whatever. Maybe it doesn't, we don't need to worry about it. So then, let me do this simple cycle first. Int I equals 0, I less than max, mean nums1, nums2, I plus plus. So the first step is to add all numbers that are in both add all unique numbers that are in both vectors, whatever vectors. So to make sure it's unique, unordered sort of int, let's call it s. Then what do we do? So basically the idea is I'm checking, let's say nums1 equals nums2, nums2 I, right? Or it's not necessarily I, it may be some j index or whatever. Oh, let's actually have two indices here. J, I, and J. I'm not sure if this syntax is supported, but whatever. J plus plus. Or just do nothing, actually, you know. We don't care. We'll increment it themselves. If equals J, if both are equals and nums1 s find nums1 equals s and, right? So there is no such element. Then what do? We say q, is it push? CPP q, example. I guess it's push. push nums I, because we know that it's equal nums 1 I, right? And then we say I plus plus j plus plus. Else, if let's say nums 1I is less than nums j, so what do? We say I plus plus, right? Else, if it's, so the rest, so we already checked if they're equal, or let's do this. Else if nums I is less than nums 2j, num size 2, and we don't need, we need this. Well, let's not use while for at all. Let's just use while. What the heck? Is less than size, and nums and j is less than nums 2 size. Right? So we start int I j, or we can say 0, 0. Right? So we also need, say, s, insert nums 1I. Or do we really need set? Because all we can track, it can be last common number, and we can start with 0 because 0 is presenting neither. Right? So, because obviously they're increasing, so that simplifies things. So we definitely know that the numbers won't repeat themselves, or if they repeat, that they will be just the last one. Okay, so let's just say int last common equals 0, and if nums I so basically all we need to do, actually, we don't need this second check. All we need to say is that if nums I equals to last common, right? Common, we do what? We increment I, and this should be nums 1. Similarly, if it's for the 2 and this is for the j, it equals last common, then we increment j. So we already know that both are not equal to last common, right? So, okay, this is the boring, and they never will be 0, so we never hit this at first. So we check the first element to first element, not equal. Here we say, okay, which one? We don't need insert. All we need is to say last common is this guy, right? So all we need to say here, and maybe make it like this, and then we can say else. Now it's, here's what's left. This is less than this. Those are equal, then increment both. This is less than this, and vice versa. Nums2 is greater than, is less than nums1. Then we need to increment nums2 until we hit the larger number that is comparable to nums1 or equal or whatever. Then we say j++. Right, so what's the worst case scenario? So the worst case scenario, if nums1 numbers are all smaller than the nums2 numbers, and in this case, we will go basically through the entire length. So the worst case here is or nums1 plus nums2, which is fine. It's still linear. I wouldn't imagine there is a faster way, even though they're sorted. Common unique values in sorted arrays, right? So now what? Now it's basically the same. So now or first find max until last common. It's okay. Last common. It's already used. So let's call it previous common here. So it's not confusing with this guy, right? So what do we mean here is that while q empty, right? What do we do? Well, we can say that these guys are 0, so we reset them. Or I guess we can do this, right? While, so we say int current common, or next common equals to q top, and then we do q pop, if I remember correctly, right? So now we need to find the maximum. So there will be 2 while cycles, while while nums1 I is less, not equal to next common, we say what? We need let's say int go max score, which is initially 0. So we say, so here will be another int max score 1 equals max score, all right? And we say what? Max score 1 plus equal nums 1 I plus plus, right? Until we hit the common. Once we hit the common, then we stop, right? Because until we hit the common, then we can transfer. So another problem is we need to count only unique numbers. So last unique one, we start with 0. All right, yeah, let's do this. Int last unique one, that is 0 or whatever. Every time we start with 0. So what do we say? If numpsci plus not equal to last unique one, right? Yeah, it's badly formatted this way, so let's move it here. So then, if it's not equal, then we add to the score, but else if it's equal, and then if it's not equal, then we say last unique equals to nums y. Oh, damn. It will be disaster. Yeah, let's say and I guess it's just better to mark it explicitly, otherwise it will be a little bit weird to have it like this. Just add extra line, it's not a big deal. To increment it. Else, just increment, right? That's what we need, so we don't need else, we just say this guy. So, and this is cycle while that ends basically nowhere, right? So we need to say it ends somewhere. Right. So count max left score. Max left score. Left, by left I mean num1. Not sure if it's left and right, but whatever. And then we do the same kind of thing. We do the same kind of thing for right score, right? Count max right score. So it's max score 2, or we can say first score, second score, but this it will be confusing with first, second steps. So yeah, it sucks. Whatever. Right, unique. Left unique one. Okay, yes, I end up. So it's max score 1 and unique 1. No need left and so count max score 1, count max score 2. And we can even say this, right? So we explicitly refer what exactly we are counting in these cycles. So it's clear. So unique 2. So this was unique 1, unique 1. Next common, okay. Now it's 2. and we have j here, right? Because now we're working with j once we work with second one. So we say unique 2 equals nums2 j, right? And it's unique 2 Right. So we done this. We count max score 2 as only unique one. Say j, 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 j. All right. So the max score here now is what? His max score here is the max between max score 1, max score 2, plus next common. All right. That's basically was the whole point, because we can transfer through this point. Now we know, okay, we transfer either this way or this way, but we already know what's the maximum achievable for this guy. So now all we need is just move ij to next unique elements. So basically we do this. So because both stopped at the point where those are equal, so we are say now basically the opposite, right? Nums 1 I equals next common, we say I plus plus. Same thing here for the j, right? And it's j plus plus, and it's 2. So nums2, 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 max score 2, unique 2, everywhere j, unique 2, except next time, obviously. Here is unique 1, unique 1, unique 1, and nums 1, max score 1. Looks like the thing. So at the end of this cycle, now we have the maximum score for the life, right? Ah, gee. And now we need the only thing left here. So it's a little bit macaroni code, and maybe it can be refactored better, but let's do this one macaroni code so far and see if it just works, because it's a hard problem. We don't have time left, basically have 2 minutes only. So it's, I would say, if you will be able to debug this now, should be fine. So all we need to do is basically exactly what we did before, but now until I less than nums1 size, right? We keep iterating. Same thing here. Count max score 2. So the only difference is now that start with this. So we part it to the place where there is not equal to next common. So we don't care. So we know this I and j won't access those elements that were last next common thing in the queue. That will be next after next common, in this case 10, in this case 9. So it should be fine. All right. So yeah, we just do the same and we just add if it's unique. If it's not unique, then we say, okay, last unique was this, and we add it to the score. Otherwise, we just part it. In both cases, we just keep iterating, but we add to the max score and track unique only if it's. Same thing here, right? We start with max score, which was the max achievable with all these jumps. And what's left at the end of the tunnel is return max, you guess it, max score 1 and max score 2. Let's see if it runs. I doubt it runs, but let's see what happens. But in both cases, it's linear. No member name top. So as usual, so what do I say then? Just pop? Front. Here we go. Front. And then pop. Next common. Did you mean previous common? Oh, no. Here should be j less than numbs size. And actually, because we don't change anything, we can say those are const as well. It won't change anything, but just for whatever thing it is. Output 29, and we expected 30. Damn, it was close. All right, so let's debug this example and see where we screwed. So for some reason it says 29 is the maximum. Interesting. Why not? All right, let's go one by one. So this one, ij zeros, right? I less than num size and j less than 2 size, then we keep finding non-unique ones. So in this case, I would imagine, let's see, let's just basically do before we increment, right? Oh, we have previous common, all right. Cout common element equals previous common. Then we pod. If numbers to j equals, then we pod, right? To first that not equals to previous common. Then we check if they're equal. Then we push something. If they're not, and if they're not equal, we don't do anything. We just iterate one or another one. And then let's also print, so we better understand what's going on here. This is what's most interesting. So cout common element, next common. All right, so then we say max score 1 equals max score 1, and same thing for 2, right? max score 2, and it's 2, and then we say new line, new line. So let's see how this works. This is weird. Oh, yes, of course. So stupid. Here we go. Sounds like it works. Sounds like it works. Let's see if we submit it and passes. All right. One more time to just make sure that we didn't comment anything viable. 30 out of 30 and submit. It's a linear time, baby. Low memory. And what? Some corner case, I guess, somewhere. Ah, here you go. Here we go. You see? So let's keep this thing up. I think once we pass this corner case, we should be fine. It should be fine. Yes, the maximum element is 7, right? Max score 1 is 6. Max score 2 is 10, and it's correct, right? So definitely it makes sense to continue with this guy. And so we exit this cycle, right? Ah, yeah, exactly. So if it's the last element and it's equal next comment, so what do? We increase it. And boom, we cannot access it. It's overflow. While obviously j less than nums2 dot size and this thing, and for this one is I and nums1 and that thing, then it should work. Right, let's see. Of course, code formatting today is terrible, but so far it works fine. So we got this 10, max score 2, right? And we had only one iteration in this common cycle. So the max score will be 17, and we start with next unique element, which is 12 here, and we say 12, 13, blah, blah, blah. We add it together. They're all unique. And then we jump to the score 2, which is j less, and j is already greater than these guys. So so the max score will remain the max score. So and then we select max score 2, max score 1. Obviously, it will be max score 1. All right. Sounds like it should pass all tests now, but we'll see. Maybe time limit exceeded or whatever. Oh, sign integer overflow. Sign integer overflow, meaning that every time we add something to math, so we should have this modular or whatever. Let's see. Modular equal what? What they say in the description, it's 10 to the power of 9. So it's right plus, so this is 7 So the nums themselves are small, so they should cause overflow. But the sum, when we start computing the max score, right? So every time we, yeah, I guess every time you add something, you should do just this. Here and there and, but this is just one value, right? It won't be able to overflow things. Will it? Yeah, every time we add something, we need to divide by modulo now. This and this. So now should be fine. Let's see. No. Sign integer overflow. Oh, it's even tells me here. Let's do differently. Let's do this. So every time we add, we remove whatever they are, right? Percent equal modular. Or maybe we can say actually this way. Oops. Plus percent modular, right? That's what we need. Same thing, I'm afraid, for this guy. Now it should be just 1, 1, 1, I. Then here, and then this thing is here. And then when we do the max score here, it technically should be max score for whatever here times modular, right? Ooh. So we make sure we can assign it. Oops. Hopefully it passes now. Now it's the wrong answer. It's what is it? No, but it works for small numbers. Interesting. So it works for almost all numbers except this. So is it the way how we... All right, let me just do stupid stuff. Let's remove all of this, right? Let's say we never done this. Thing, right? We just do this, and we just say this. No thanks to this. Let's just say those are long, long. So double long, right? And this guy here is long, long. And this guy here is the long, long, right? And we just add them directly without worrying of anything, like completely. But so where do we use it? Let's say again, this is long, long, and this one is long, long. And then we say plus equal, no thanks to this guy. I just want to make sure, because it passed almost every test, and now it fails here. And it looks super weird to me, just because it might be something related to this modular stuff. Maybe there is some number that is offset by this one, and that's why missing this large one here. So that's why I want to make sure it's modular, right? And all we need is this percent modular here, modular here. All right, submit. Ladies and gentlemen, I would still count it as under 40 minutes, although we spent a little bit time on the debugging, but we passed it. We cracked this hard problem today, which is basically, I guess, the first time. Now let me see, so it doesn't count for the time, so I will just run several times to see what are the best numbers I can get here. Oh, all right, 96 milliseconds and 55.9 megabytes. Not bad. For the hard problem, it's not bad. For the hard problem, it's not bad to solve it. Not saying, of course, I solved it. Okay, so it seems like the best so far is this and this, so after 3 runs. So let's see when this combination appears. If at all. No? All right, one more time. Whoa, even better. The best time ever I've had. So it's 97 and 36 points. 97 for time, 36 for memory. So time is linear, memory, the code is crap. Super, look at that. Oh my gosh. But again, this is the hard problem. So you can discount this code formatting and debugging time we spent extra. It's okay. We cracked the algorithm itself under 40 minutes, and we were able to code it under 40 minutes, and then the rest was just, minor stuff. So let's switch to the whiteboard with those numbers. Where's my mouse? Nope, nope. I wonder if there is some hotkey to change it, but whatever. So today we did it like a boss. Oops. We cracked it, the hard problem with good numbers, relatively. Yeah, those are good. It's more than 100 points combined for the hard problem, and we basically fit into the time again, except stuff, but that's okay. Debugging is always okay, because if you let's say do an on-site interview, you do this on the paper, right? So nobody will actually go through all these corner cases and say, oh, you know what, in this specific case the corner case doesn't work, so you forgot to pad it by one, or like in this case we said, oh, while should we also take into account that we can validate the length of the array or something like that. Or this modular stuff, nobody actually will even ask you for the modular stuff or say, oh, it can overflow, so be careful. No, but for the lead code, it's okay. So we don't take this time to greenlight the code itself that was written under 40 minutes under account. So it's 133. And today we actually, I'm not sure if I remember correctly. This we act like a boss, right? I'm not sure if it's the way you should put a smile like this, or maybe it was. Sorry, maybe it was. Um, so the bigger glasses. Nah, it doesn't look like a boss. So let's keep this one. Success. So today I even have a mood to go and show some fireworks and see some fireworks. Sorry. All right. So YouTube. Where is the YouTube? Show me the best fireworks ever. Oh wow, looks cool. Let's see what that. Oh, damn. That was cool. So thanks everyone, and hopefully see you next time, like tomorrow.